Okay, let's unpack this. Welcome to the deep dive. We're diving into your sources today on set theory.
Yeah, taking the material you've given us and really getting into the fundamentals.
Exactly. Our mission is to see what these sources highlight as, the core ideas, the important distinctions they make.
And it's interesting how they start. It's all about this precise language for, well, collections of things. You might think you know sets, but the sources really stress this idea of being well-defined.
Right, that jumped out. It's not just grabbing any bunch of things. So, what makes a collection well-defined according to these sources? Can you give those examples?
Sure. So the classic example they contrast is tall students.
Yeah.
That's not well-defined because, well, what's tall? It's subjective.
Okay, yeah, no clear yes or no.
Exactly. But then they give something like students with heights between 135 centimeters and 160 centimeters. That is well-defined. You can measure. There's a clear rule. You're either in or you're out. No ambiguity.
Got it. So that clear criteria is the key. And the things in that well-defined collection, those are the element.
Yeah.
Or members.
Precisely. Elements or members. And the notation follows, right? The sources show sets usually get capital letters. Elements go inside curly braces.
Yeah.
Like set A, John, Gita, Amit, Rohit.
Okay. And those symbols, sure, belongs to and DF4 does not belong to. Pretty straightforward.
Yeah, basic tools for saying what's in the set.
So once we know what a set is, how do the sources say we actually, write them down? There were two main ways mentioned. First is the roster form or tabular form. Basically, you just list the elements out. Simple as that.
Like the examples they gave for integer Z, whole numbers W, natural numbers N.
Exactly. $1, $1, and $1, $3, $3, and so on. But there are rules here the sources point out.
Oh.
Yeah, two key things. First, the order you list them in doesn't matter. ABC is exactly the same set as BAC.
Okay.
And second, you only write each unique element once. So like the letters in Allahabad, you wouldn't write A multiple times. The set is just ALHBD.
Ah, interesting. So it's about what's in it, not how many times, or the order. Makes sense. What's the other method? That's the set builder form.
Yeah.
Sometimes called the rule method. This one's really useful when listing is impossible, like with infinite sets or just awkward.
How does that look?
Use a variant like X rule about X. At colon, say E just means such that.
So for natural numbers less than 7, instead of listing 1, 2, 3, 4, 5, 6, you'd write X is a natural number and X and 7. Or maybe using the symbols X and an N, text and I7.
Exactly that. Or the example 2 through 55 could be X and N 2 by 6. It defines the set by the property its members share. Very powerful concept highlighted in the sources.
Right. Okay, shifting gears slightly. The sources also cover some key concepts about sets, like cardinal number.
Yeah, that's just how many elements are in the set. Simple
Yeah.
count. We write it NA. So if A, C, D, F, then NA is just the size.
Gotcha. And then types of sets, finite, infinite, those seem clear. But the empty set seemed to get special attention in the sources.
It did, and for good reason. It trips people up. The empty set, written empty set, or just has 0 elements, then empty
That's
set.
simple enough.
But the sources make a point to say the set is not empty. It contains one element, the number 0. So its cardinal number is 1.
Ah, okay. That's a difference.
And even trickier, the empty set isn't empty either. It contains one element, the empty set itself. So its cardinal number is also 1. These distinctions are really important in formal set theory.
Wow, okay. That's subtle but critical. What about how sets relate to each other? Subsets.
Right. If all the elements of set A are also found in set B, then A is a subset of B. We write one subset take B. The sources used a $2, $6, and $4, $5, $6, and $7. Since 5, 6, and 7 are all in B, A is a subset of B.
Makes sense. And the sources mentioned 2 facts about subsets.
Every set is a subset of the set Getty set, and the empty set is a subset of every single set. Those are fundamental rules.
Okay. And what's a proper subset?
Similar, but stricter. A is a proper subset of B, D subset B if it's a subset, and B has at least one element that isn't in A. They can't be identical.
Ah, so like the natural numbers n, 1, 2, 3 being a proper subset of whole numbers w, 0, 1, 2, 3, because w has 0 and n doesn't.
Precisely. N euro W. And of course, no set can be a proper subset of itself.
Got it. And superset is just the flip side. If y dollar subsec of b, then b is the superset of a, y dollar subsec of a.
Exactly. Now, the universal set, 6LRU.
Right. What's the deal with that?
It's basically the universe for a specific problem or discussion. It contains all the elements you're currently interested in. If you're working with sets like 5, 6, 7, 8, and 1, 3, 5, 7, your universal set might be 1, 2, headed, 10, or maybe just all integers. The key thing the sources note is that the choice isn't always unique. It depends on the context.
Provides boundaries for the discussion.
Okay.
And complement. A prime.
A is everything in the universal set that is not in set A. So if your universe cap is 1, 3, 3 others, 4, 3 others, and 5, and A is 2, 3, 3 others, and A is 146.
The leftovers.
Sort of, yeah. And two key facts from the sources. A and A together make up the whole universal set, and they have nothing in common. They're just joint.
Okay, that covers relationships. The sources also briefly touched on operations, right? Union and intersection.
Yeah, quickly. Union, wall cut B, is everything that's in A or in B or in both. Combine them, but don't list duplicates. $5 gives you $6. $6 is $7.
Got it all together.
And intersection, cut par B, is only what they have in common, the overlap. So $5, $6 is just a
shared element.
Right. And if the intersection is the empty set, cut pay B, empty set, then the sets are called disjoint, no overlap at all.
Phew. Okay, so we went from the absolute basic what is a set, that need for it to be well defined through how we write them, the different types, how they relate, subsets, complements, and these basic operations. Seems like the sources build a really clear picture.
Yeah, it's about building that precise language. The value, I think, is seeing how carefully these definitions are constructed to avoid ambiguity. It's rigorous.
Definitely. So thinking about that rigor, here's something to leave you with. We talked about that really fine distinction between the empty set, the set containing 0, and the set containing the empty set. It highlights extreme precision. Where else, outside of math maybe, could paying super close attention to seemingly small distinctions in definitions or categories actually make a big difference in understanding or, avoiding confusion? Something to think about.